Okay, these are the notes on heat and temperature. So you can see this is what the note sheet will look like that you'll be taking. So heat is just a flow of energy from an object at a higher temperature to an object at a lower temperature. We've already learned that heat is a type of energy off of Mr. Scent. Remember, it's the T, it's the thermal energy. One of the things that you do need to understand, and we talked about this when we did the first lab, is that warm energy or hot energy transfers down to cold. So heat is always moving from the hotter temperature to the colder temperature. Temperature is actually a measure of the average kinetic energy of all the particles in an object. So when you actually put a thermometer in an object, it's measuring how fast are those molecules moving. So in this case, if you have a hot object, the molecules are moving faster, so you'd have a higher temperature. And if the molecules are moving slower, you'd have a colder temperature. So more motion means more kinetic energy. And just so you know, we measure all of our temperatures in the scientific scale in metric units. It would be in degrees Celsius or Kelvin, which we'll talk a little bit more about those temperature scales later. We don't really use degrees Fahrenheit in science. That's an older, outdated unit model. Celsius is easier because it's easy to remember that water freezes at 0 degrees Celsius and water boils at 100 degrees Celsius. You guys will actually be watching the Eureka clip on your own in the independent activities, so we're just going to keep moving here. So like we talked about, heat is thermal energy from Mr. Scent. Thermal energy is actually referring to the total amount of energy in an object. There is going to be a Eureka video that you're going to watch on your own that'll talk a little bit more about this thermal energy, so I won't go into too much details. But the idea is the more of a substance you have, that there could be more energy in that substance. For example, if I was trying to heat up a swimming pool by adding more water, it would be more effective to add a huge bucket full of hot water than it would to add a small cup full of hot water. So the more you have, the more energy. Another thing that we looked at when we did the phase change lab was the fact that things eventually reach thermal equilibrium. And thermal equilibrium is when an object that's at a different temperature transfers heat until they reach the same temperature. So if I leave my hot coffee out on the table for several hours and I forget about it, eventually the heat transfer is going to cause the coffee to become the same temperature as the air around it. So they'll keep transferring heat from hot to cold until they're the same temperature. Just a quick reminder that when we're talking about these particles or these molecules that are in motion, we're referring to the particles that make up matter. So that's solids, liquids, and gases. So remember, solids, the particles are in fact moving. The table that you're sitting at right now has particles that are moving. They just can't move in different positions. They're vibrating kind of in place. Liquids, because they can flow, the particles move quite a bit and they move around. And then gases, the particles are very spread out, so they can move much faster. So that's why if you think about ice melting into liquid and then a liquid boiling into steam, the higher temperatures are associated with faster moving molecules. And this is just kind of a picture to show how a solid has rigid structure and shape. Liquid takes the shape of its container, and gas, the particles tend to spread out and therefore they're moving much quicker. So let's talk about the three types of energy transfer that we looked at in different lab activities. First of all, conduction. This is when you had the metal and plastic and wooden rods in the hot coffee water. So conduction is a transfer of thermal energy from one particle to the next, and that means that there has to be direct contact. You have to be touching. So remember, you were actually touching with your fingers the rods to feel the heat. Faster moving molecules, they're going to transfer their kinetic energy to slower ones. You see a theme here. We keep talking about faster to slower, high to low, hot to cold. So again, it has to be in direct contact. We're actually going to do a performance assessment next week where we're going to be talking about conductors and insulators. So remember that a conductor is an object that easily transfers energy It could be heat, it could be electricity. Insulators impede or at least slow down thermal energy. So think of a conductor like touching a hot metal pan, but an insulator being the pot holder or the oven mitt that you used. So it blocks the heat so you can pick up that hot pan or cookie sheet. Your jacket that you wear acts as an insulator, but if you are sweating, it acts as a conductor. When you're sweating, the actual moisture that appears on your skin is helping to conduct some of the heat out of your body and exchange it with the air, which is probably cooler than you are. The other one we did was the convection. That was the water bottles, hot on top, cold on bottom, and then cold on top. Actually, we did cold on top, hot on bottom first. And remember when we did that lab, you saw that when the cold was on top and the hot was on bottom, you saw lots of mixing occur. The second time, when you put the hot water on top with the food coloring and the cold water on bottom, you saw little, if any, mixing occur. Now, why is that? That's because we know the second point here. When fluids are heated, a fluid expands and it becomes less dense, and therefore it floats. We'll talk more about density in another unit, but density is just talking about how tightly packed those particles are. So the more space there is between particles, the less dense something is, and it tends to float up. Okay? When a fluid, gas or liquid, cools, it becomes a little bit more dense, and therefore it sinks down. So when we put the cold water on top, it was more dense, so as soon as it had the passageway to do so, it flowed down to the bottom, and the hot water was less dense, so it pushed up to the top, and you saw lots of mixing occur. This happens in ocean currents. It causes the water fluid to mix pretty well. And we talked a little bit about how this also forms some weather patterns. So whenever you have actual weather going on, where there's like a storm, there's some wind, even rain, that's usually formed by those convection currents, where the air gets heated by the actual surface of the Earth and goes up, and then as it cools off, it starts working its way down, and it actually makes a almost circular or cyclical motion, and that causes air patterns. And of course, your oven does the same thing. That's why the burner's on the bottom of the oven, and so the hot air that gets hot because of the burner at the bottom goes up to the top of the oven, and then as it cools, it sinks back down, and there's constant motion in your oven. So if you've ever opened up the oven while it's cooking in there and that burst of hot air comes at your face, it's because the air is actually moving quite quickly in there. And then lastly, radiation. You guys are pretty familiar with this. We did the little white and black box experiment while you guys were also doing phase changes, and we found that the black box absorbed 4 or 5 degrees of more heat than the white box did, because the black absorbs heat, white reflects it. But radiation is just the transfer of energy that travels as an electromagnetic wave. So that can be anything from radio, micro, infrared, visible, and also ultraviolet, X-ray, and gamma rays. The sun is the most significant source of radiation we experience daily. Think about the sun heating up the earth and providing us the energy we need to survive. And that is it for your notes on conduction, convection, and radiation. Make sure you glue these in on page 39.